All right, let's do some basic u substitution and some non-basic u substitution. A lot of this is going to be thinking about what will be an appropriate guess for the value of u. So for part one, I'm going to allow u to be, what is the exponent of e? So minus 4x. Taking a derivative of that, I can say du would be negative 4 dx, treating it in the differential form where the du and the dx are on different sides. Now, I could do one of two things. Noticing there's no negative 4 constant in the equation, I can either put one there and divide by negative 4, or I can just simplify this and call that negative 4, or 1 over negative 4 du is equal to dx. With that, I can then substitute in to the original equation and get e to the u equals du with 1 over negative 4. Since it's a constant, I'm going to put it out in front of the integral symbol. I could have put it inside it as well if I had chosen. And the integral of e to the u is just e to the u, so this is negative 1/4 e to the u, or in this case, u is minus 4x plus a constant. For step 2, you just plug in the 8 and the 0 to what you did in the part before, so it would be negative 1/4 e to the negative 4 times 8 is 32 minus negative 1/4 e to the 0. And then you solve that for the particular value given in the solutions. For this problem, an appropriate guess for u will in fact be what's inside of this here, since if I call u x cubed minus 6x, what's going to come out of that is that 3x squared minus 6 dx is the derivative. Now 3x squared minus 6 is the right form for this. It's off by a constant. Notice that if I multiply this by 3, and if I divide by 3, then I could just substitute this in directly. So this integral becomes 1/3 3x squared minus 6 dx all becomes du, and u to the 207. 1/3 hangs out, integrating, we get 2 u to the power of 208 divided by 208 plus a constant. And you can simplify that a little bit, as well as in the solutions. Let's let u be what's up top. Then du is negative sine x dx. Super close to this. It's just off by a negative. So when I substitute this in, I'm going to get a negative e to the u du. So negative e to the cosine x plus a constant is my answer. For part 5, just plug in those values. So it'd be negative e to the cosine of pi halves minus negative e, so plus e to the cosine of 0. Cosine of pi halves is 0. Cosine of 0 is 1, so e to the 1. All right, let's take a few more here. Looking at the numerator, I have a constant and an x. Well, that would come out of the derivative of an x squared. So let's set u as x squared plus 1. du would end up being 2x plus 1. Or sorry, not plus 1, just 2x dx. So I'm going to divide by that 2 to get everything looking just how I like it. This problem then becomes the integral of, well, u to the 7 is in the denominator. X dx turns into, well, the 3 is coming along for the ride. X dx is du over 2. The 3 halves, the 3 and the 2 come out. And I have the integral of u, I'm just going to call it u to the negative 7 du, which you can solve pretty quickly as you add 1 to the exponent, divide by that, plus a constant. And you can simplify that as well. Keep going. Some good guesses for you is the denominator here, x to the fourth plus 1, du would be 12x cubed, which is exactly what's up top. So my integral is just, excuse me, with the dx there, 1 over u du, so natural log of u, in this case, natural log of u, where u is 3x to the fourth plus 1, plus a constant for good measure. These are getting pretty fun here. This is a nasty exponent, but notice the part out front is a lot like what's up there. The derivative of what's up there, at least. So if I let the exponent be negative 3x squared plus 8x, let that be our u, then the du is negative 6x plus 8. If I cut that in half, I'd have du over 2 is negative 3x plus 4. Excuse me, I should have kept the dx along with us here. So that changes this whole thing into, well, the first part with the dx turns into du over 2. I'm going to put the 1/2 out in front. The du's in here, and it's e to the u. And so it's old hat. Continue from there to get the solution. For the sake of this, number 9, once you get the solution to 8, you plug in the 2. And then you subtract off when you plug in the 0. Let's do number 10. Number 10, my first guess for you would really be the denominator, x squared plus 1, giving me du is equal to 2x. Now notice that's not quite right with what we have here. So what does one do in this situation? We have some options. We could first really split this up into 2 different integrals. And so let's do that. So let's really think this could really be an x over x squared plus 1 plus 5 over x squared plus 1 dx. And when you have an addition there, you could actually split that up into 2 separate integrals entirely, right? Because you're allowed to distribute the integral sign over addition. All right, so in this form, now we're a little bit more set up for the substitution I recommended ahead of time. So for the first integral, notice I do have an x and a dx. So if I divide both of these by 2, then I realize I left that off too. I'm in a bit of a rush trying to get through these problems, and I keep letting the dx hang. That should have been there. I'm sure you noticed that. You little smart kids, you. Excuse me. So that would give me, for this first one, if I do that substitution, x dx turns into a du over 2. I'll put that out in front, the 1/2, and 1 over u. I'm just going to continue down and do this one by itself. So the 1/2 coming along for the ride. 1 over u turns to natural log of u. But we know u is in fact x squared plus 1. So that's 2 steps. It's the natural log of u. And the u changes back into its form of x squared plus 1. Now the second one is a little bit more tricksy. So the second one here, I'm going to pull the 5 out in front and have 1 over x squared plus 1 dx. This is one that we've done before, and so if you recall, great. Otherwise, we can just remind you it's the inverse tangent of x, and we have to add an arbitrary constant here. Great. Let's go some more. Looking at 11, one thing that's funny about math and fractions is that often addition in the denominator is really annoying, where addition in the numerator is not that annoying. So there's a handful of ways you can do this one. I don't actually know what the thing says you should do. What I would do is this. I would, in fact, do one of two things. I could just let u be the denominator, e to the x plus 1. And that's what I would, in fact, am going to do right here. Two ways I can handle this. This one, it works out when you do the du. You just get the e to the x dx. And so that really simplifies this one right here as du with a 1 over u. All right, so it's the natural log of u plus a constant, but in this case, u is e to the x plus 1 plus a constant. Now, sometimes, even if I did not have e to the x up top, this could still be a good idea to let u be the whole denominator. And sometimes, it changes the addition that was in the denominator to the numerator, and then you can split it up into different fractions. That is sometimes a solution. It's not needed here, though. This is us doing this in real time. All right, so this one, I'm looking sine to the fifth. There's a composed function, so my instinct says let it be sine, and the cosine on the outside, being the derivative of sine, confirms that suspicion. So let's just go ahead and say if u is my sine of x, well then du is cosine of x dx, and this whole problem just turns into a u to the fifth du problem, which is u to the 6 over 6 plus a constant, and we know that u is in fact sine. So sine of x to the power of 6 divided by 6 plus an arbitrary constant. Great. So then we're going to look at number 13. So this one you have a square root with some x's down below. So you might think maybe it's just going to be u equaling x plus 1. That'd be my first guess. And let's see how this works out. Now, du just turns into dx. And at first you're like, oh, shoot. I really wish I had an x in here so I can just get a nice, du up top and everything would have been great. We don't have that here. In fact, we end up with this du. It's like you have an x up there, then you have down below a square root of u. And you're like, oh, dang it, I have this x. Do I give up? Maybe, although notice this. In my equation for u, it also gives me an expression for x if I subtract 1. So u minus 1 is equal to x. And this goes back to what I was thinking about in the problem a couple before, is that x is really u minus 1, which allows me then to take that addition that was in the denominator, put it in the numerator, in this case as subtraction, do u divided by root u minus 1 over root u du. And this changes that more complex thing into two simpler problems, because the first one is really just u to the 1/2 minus u to the negative 1/2. And for both of these, they follow the same pattern. Add 1, so u to the 3/2, divide by 3/2, which is the same as multiply by 2/3, minus add 1 to the negative 1/2, u to the 1/2, divide by 1/2, which is the same as multiply by 2, plus a constant. And then all we need to do for the very last step is remember that u was x plus 1, and so we just copy down most of that, where it turns to x plus 1 to 3/2 minus 2 x plus 1 to the 1/2, plus the good old arbitrary constant. We'll make a little bit of a calligraphic capital letter there, just for fun. And I think this video is at time.